Hello, welcome to another video. In this one we're going to do some examples over 2D kinematics to kind of get you going, kind of get you ready for doing these types of problems. By and large I can't, cover every sort of example you'll see, but I think this selection of questions that I've chosen is a pretty good selection. So, let's look at this first example that I've already posted here. So a movie stunt driver on a motorcycle speeds horizontally off a 50-meter high cliff. And we want to know how fast must the motorcycle leave the cliff top to land on the level ground below, 90 meters from the base of the cliff where the cameras are. Okay, so the first thing that we're going to do is probably what I'm going to do for most examples is actually draw the situation. So we've got a movie stunt driver on a motorcycle and they're speeding horizontally off a cliff. Okay, so this guy's, on a motorcycle, right? I don't know how to draw one just off the top of my head, but something like this, okay? And he's going this way horizontally, okay? We'll see that that's a key word for us soon. But they're saying how fast must they leave the cliff top? So we don't know what this guy is. What else does it tell us? 50-meter high cliff. So that means we need to set up our coordinate system. And what I'm going to do for our coordinate system is I'm going to say the origin's down here. And so I'm going to put this right here for our origin. Okay. You could certainly set the origin up here. But in doing this, origin means that y initial now is down here. Y final is at 0 because he's going to follow this trajectory, okay? And so y final will be at 0, whereas y initial will be at 50. You could make this the origin, which would make this 0, this negative 50. So however you want to do it. They say the cameras are 90 meters from the base of the cliff where the cameras are, which is where he's landing. Cameras look something like that. I don't know. So this is x final is 90 meters from that, okay, because that's the length of that. And so x initial would be 0. All right. What else does it tell us? We went through position. We looked at v initial where it tells us it's horizontal. So we've done that, and I'll talk about what this means when we do knowns and unknowns. Time, we don't know. And since we've made up positive here from 0 to 50, so we've made up positive, that means A will be minus 9.8 meters per second squared in the y direction. Okay, so now let's do knowns and unknowns. So, x initial is 0, x final is 90, y initial is 50, y final is 0. Okay, so these were all numbers that we wrote down. We go into our v. Okay, so there's 3 types of v, right? There's their v initial, there's v naught x, and v naught y. Now, it told us horizontally. That means there's no vertical component. So this will be 0. So v naught y is 0. There's no vertical component because it said horizontal. Okay. So always look for keywords like that. Even if it said, vertical, right? Then it would say, okay, there's no v naught x, right? So now that means all we're looking for is, since it's horizontal, we're still looking for v naught, but v naught is equal to v naught x because it's horizontal. But we don't know what these guys are. But we do know they're equal to each other. We also don't know time, and we do know our acceleration. Okay. and I'll explicitly write this, it is only in the y direction. There's no acceleration in the x. So these are, knowns and unknowns, okay? So now we want v naught x, right? Which means there's only one equation on our list that has v naught x in it. This one. And so what we should do, that guy's 0. So this is our equation. So we should solve for v naught x. Well, v naught x equals x final over time. Okay? We don't know time. So we need time. We, of course, have x final. That's equal to 90 meters, right? So we have x final, but we don't have time. There is one other equation with v naught x, actually. It's v naught cosine theta, but we don't know this. Okay? And, in fact, cosine of theta, there's no angle because it's horizontal, so it'd be cosine of 0, which is just 1. So v naught x equals v naught. So this equation doesn't even help us. So there's no way around it. We need time. And that's typically how these problems will flow. You'll get time in one coordinate and then plug it into the other. So in this case, we're going to get time from y. So the major time equation, or the major y equation that we'll use, is this guy, typically. Maybe we'll mess around with the v finals, but this is typically what we'll do. Y final is 0. Y initial was 50, right? Because we're going from 50 to 0. This guy is gone because v naught y was 0. So this tells us 0 y initial plus 1/2 at squared. So we just need to solve for time. Okay. So minus y initial is 1/2 at squared. Multiply by 2 and divide by a. So that means our time is the square root of 2y0 over a. Negative. So 2 minus 50 meters over minus 9.8 meters per second squared. The meters will cancel, we'll get units of seconds. This is roughly going to be the square root of 10. What do I get for that? T equals plus or minus 3.19 seconds. We're going to take the plus. We encountered multiple solutions for time in one-dimensional, where that just means instead of going forward, you'd literally just be going backwards. Okay, it's symmetric motion, so that's why we get that. But it's a nonsensical solution for us. So our time is 3.19 seconds. So now, plug time back into x. So x equation was x final. Well, we already had solved this, right? Where we had solved for v naught x. So v naught x was x final over t. And so we're going to take that, plug it in there. So v naught x is equal to, I believe it was 90 meters over 3.19 seconds. And this gives us our v naught x of 28.2, okay, which is our answer. So let's just real quick do a summary of this guy. So we had this problem, which we drew out, and we needed the v naught off the cliff, which we surmised, because of the word horizontal, is equal to v naught x. So we needed to solve v naught x. The only useful equation that has v naught x in it for us right now was this one. We solved it, realized we need time. So we go to the y equations for time, solve for time, plug back in to get v naught x. And again, that's how it will work. Sometimes you will have time, sometimes you'll solve for time in the x, plug it back into y, or things like that, okay? That's definitely a lot of these problems, but not all of them. So let's go ahead and look at another example. So that prior example was going above to below, right? So example 1 was above to below. This one that we're going to look at is level. Okay, so, and then we have one, the last one that we're going to look at is below to above. So this is example 2. And here's the example. A kicked football leaves the ground at an angle of 37 degrees with a velocity of 20 meters per second. We want to calculate the maximum height, the time of travel before the football hits the ground, and how far away it hits the ground. So let's look at this. So here's my football. We're kicking it, okay? V naught, and this angle is 37. Whoops. V naught equals 20 meters per second. This is its trajectory. Okay. It's going to land over there. This right here is the maximum height. I'm just going to call it Y max. We don't know what it is. We don't know the time of travel. And we don't know X final. Okay. What else? We can say Y initial is 0. We can say Y final is 0, right? Because they're launching and ending at the same height. X initial will also be 0. Okay, so let's go ahead and map this out. So we've got knowns and unknowns. X initial I said was 0. X final is an unknown. We've got Y initial is 0. Y final is 0. V naught, we know, is 20 meters per second. Theta, we know, is 37 degrees. We don't know V naught X, and we don't know V naught Y. A is minus 9.8 meters per second squared. I'm just going to define up as positive here. And time we don't know. Okay. So I went through positions, velocities, then acceleration, time, and any other extraneous stuff. We don't know Y max. Sorry. That was another position. Okay. So, there's a couple ways to approach this. We can actually get X final first if we use the range formula. I think that's fine. We can just go ahead and do this real quick. It doesn't take too much time. And we can use this because Y initial equals Y final. Okay, you need that to be able to use this. So we can go ahead and plug that in. Uh, 37.2, which is what, 74 degrees? And then 9.8. Remember, actually, that you don't make this negative because the negative is pulled out when you're deriving this formula. So you always use a positive one here. And you get 39.2. Cool. I usually recommend, if you need this, if you need X final when you're trying to do this and you have a level thing, to just start with the range formula. It's super easy. You just plug in, you get that right away. So we now have X final. We have that really quickly. Another thing was time of travel. And since we have X final, we can use the simplest formula. The x equation really is the simplest one. That guy was 0. And so we can get v naught x times time, right? We have this guy. We can get this, and we have time. So now, let's go ahead and solve for v naught x. So v naught x is equal to v naught cosine theta. Okay, it's actually not that bad. So we plug in. Again, make sure your calculator is set to degrees. Otherwise, you're going to get not the solution we're looking for. And this is 16 meters per second here. And so we just going to solve for this now. So x final equals v naught x time. So solve for time. So time equals x final over v naught x. X final was, I've already forgotten, 39.2. So that's meters over 16 meters per second. The meters here will cancel and you'll get units of seconds. 2.45. Cool. So now we want to solve for the peak of the motion. So there's a few ways you could do that. There's a couple ways actually. Let's just write down an equation and figure out what the easiest one would be. This equation right here would work. You could probably also use this equation right here because this also has, you know, solve for y in this. And then you would use the fact that v final y at the peak is also 0. But since we already have time, let's just go ahead and use this guy right here. So y peak equals y initial plus v naught y t. We're going to have to solve for v naught y plus 1/2 at squared. So y initial actually is 0. And then v naught y, let's just go ahead and solve for that now. Sorry. So v naught y is v naught sine theta, which is 20 sine 37 degrees, and this is roughly 12 meters per second. So y peak then will be 12 meters per second times our time. So what's our time going to be? Well, our time right here is 2.45. So the peak of the motion, right, actually occurs at half time. Right? So this is 2.45 seconds. This would be half of that, which is roughly 1.225. So we're going to use 1.225 seconds here. Okay. Plus 1/2 minus 9.8 meters per second squared. Whoops. Times our time, which is 1.225 seconds, and that's squared. So you got 12. You multiply that out, and so this is going to be 12 times 1.225 minus 4.9 times 1.225 squared, and this equals 7.35 meters. Okay. And so that's the peak of the motion. Okay. So now let's go ahead and solve another example. This is our third example. Okay. So this is going to be a rescue plane. So here's our example. So a rescue plane wants to drop supplies to isolated mountain climbers on a rocky ridge 235 meters below. And if the plane is traveling horizontally, there's that word again, with a speed of 69.4 meters per second, how far in advance of the recipients, so horizontal distance, because far could be interpreted as time, must the goods be dropped? So we need to set up another coordinate system here that kind of looks like this, and you've got the survivors down here. And how far in advance horizontally. So we don't know this x distance right here. We actually don't know what this is, which means x final, we don't know. X initial we can define as 0. Let's go ahead and make y initial, let's go ahead and make y final 0. And then we'll make y initial 235, because they say 235 for that. We've got a plane. That's moving, okay? And it's moving this way at 69.4 meters per second. And so it's going to drop off supplies, and that'll be a trajectory like that, okay? What else does it tell us? We don't know anything about time. Okay, let's go ahead and do our knowns and unknowns with that information. Okay. So, x initial we said was 0. X final we don't know. Y initial is actually 235 because we said y final would be 0. V naught x is 69.4 meters per second. We have a 0 for V naught y because it's moving horizontally. And then we don't know time, and acceleration. Okay, so let's go ahead and let's solve it. So we need x final, right? So let's start with this equation. Well, we don't know it, or we don't know this and we don't know that. We know v naught x, so we're ultimately going to need to get time. So let's look at the y equations. Yeah, this looks like the guy, so solve for time. It's going to be very similar to our first example. So y final was 0 because y initial was 235. V naught y is 0. Okay, so we have 0 equals y initial plus 1/2 at squared. Solving for time. Looks like this, so it's going to be minus 2 y naught over a square root equals time. Very similar, if not the exact same. As the first example. So time ends up being 6.925 seconds. And so x final due to that will be 69.4. All right, cool. So not a long example. You just do what we did in the first example. So that's 481 meters. All right. But now, so for example 4, So this changes. Okay. Oh. There we go. So here's example 4. Suppose the rescue plane in example 3 releases the supplies a horizontal distance of 425 meters in advance of the mountain climbers. And we want to know what vertical velocity up or down should the supplies be given so that they arrive precisely at the climber's position. So this is a bit different because we now have a v naught y. So if we draw this again, okay, and there are 425 in front of it. So this is now x final. This whole thing is 425. X initial is equal, or 0. Y initial. Oops, that's Y final. Uh, 235. Here, sorry. I just can't shove it over there. So Y initial equals 235. And now what's going to happen is, well, so we've still got this horizontal, so we've still got a v naught x equals 69.4. But now we're going to have a v naught y, and we don't know if it's going to be up or down. So that's the question, right? What vertical velocity up or down should the supplies be given? And so we don't know. Or if it's up or down. Okay, so with that new information, let's try and figure this out. Okay, so the one new thing that we know is now we're being stipulated to 425 meters, whereas before we were solving for it, so 481. So we can kind of hypothesize here if we released it before that, right? So in the initial problem we had more time to release it, which means we could just go horizontal. So now that we have less time, we're probably going to have a downward velocity because, yeah, there's less time for it to reach the climbers now. But let's see if we can solve for this, because we've never really done a problem where v naught y is not 0 yet. So y initial is 235 meters, y final is 0, x initial is 0, x final is 425 meters. It's known now. We don't know time in this new instance. We know v naught x is still 69.4, but now we need a v naught y, and we don't know what this is. Okay, so we need this. That's what we want to solve for. Our acceleration, still down. Okay, so what we can do is we need y final, or we need v naught y, right? So v naught y is in this equation, as well as in v naught sine theta. So here's the two equations with v naught y. We don't know angle, actually. So we can't even use this guy. This guy, not useful to us. And we don't know v naught. So it's not useful, right? Because we don't know these two things. So we can't really use that. But we can use this guy. The problem is we need time. So y final is going to be 0 here. And so we've got 0 equals y naught plus v naught yt plus 1/2 at squared. In the previous example, this guy went to 0, but that's not the case here. That's what we're trying to solve for. So what we need to do is subtract this over and subtract over the 1/2 at squared, and then we need to divide it by t. So v naught y will equal minus y initial, which we know, minus 1/2 a, which we know, t squared we don't, and this t we don't. So this is the equation that we'll use. So now we need time to solve for this. So, like I've said, you get time from the other coordinate. So in this case, the x coordinate, which only has one formula, this one. Thankfully, we know x final. We know v naught x. We can solve for time. 425 meters over 69.4 meters per second. So our time should be less than it was before, and indeed it is. It's 6.12 seconds, whereas in the previous one, it was a bit longer, 6.9, and that's because we were farther back. So the supplies had more time to reach the people. So here's our time. Okay, so now we can just plug everything in. Minus, it was initially 235 up, okay, minus 1/2, minus 9.8, I'll make that positive, t is 6.12 squared, okay, or here, let's do it this way, put the seconds inside and then square, and then we have 6.12 seconds down here. So I actually get a negative value from this, which is what we said we'd expect, a down throw, because there's less time for the supplies to reach them. So we need to throw it downward to make it happen. Oops. So that's our answer. Okay. There's one more example that I want to do with you, and this will be the quadratic formula one. So we will need the quadratic formula for this example. Okay. All right, so a soccer ball is kicked with a speed of 27 meters per second at an angle of 45 degrees. So let's draw that like this. 45 degrees, 27 meters per second. Okay. And it lands on the flat roof of a nearby tall building. Ignore the fact that the ball is literally like a fourth of the size of the building, please. And they said the roof is, so this guy is 12 meters tall, so let's make y final 12 meters. And then y initial is 0. Let's make x initial 0 over here. X final is, we don't know x final, actually. So, this is the situation. We want to know how long does it take. So we need time. How long does it take to land on the building? And how far away is the building? So we need both of those. So knowns and unknowns. Okay. So x initial is 0. X final, we don't know. Y initial is 0. Y final is 12 meters. That's the height of the building. That's what we're trying to get at. We do not know v naught x or v naught y, but we do know v naught. and that was 27 meters per second. And we know theta. Theta was 45 degrees. What else? We don't know time. Like I said, we don't know v naught x or v naught y. We'll probably need those guys. This is what we need to solve for, ultimately. A is minus 9.8 again. That's everything. Okay, so we ultimately need y final. Okay, or we ultimately need time and x final. So if you look at the x final equation, we can get this. We don't know this, we don't know this, and we don't have a way to get it. So we can't use this now. We need to use the y formula. And if you go ahead and get your v naught y, sine of 45, this will tell us 19.1, okay, meters per second. So let's go ahead and just write all of this down and see what's up. So and I'll show you why this is problematic. So y initial is 0. So what we end up getting is y final equals v naught yt plus 1/2 at squared. And none of this is 0. So what we do is we're going to subtract this over, and I'm going to rearrange the formula. So this is equivalent to this. Now, if you remember what a quadratic formula or what a quadratic equation looks like, or a quadratic function looks like, it takes on the form ax squared plus bx plus c equals 0. v naught y is b, 1/2 a is a, and minus y final is c. Whereas time serves as our variable that we're solving for, okay, because we're solving for time. So this is mathematically why it's quadratic. So mathematically, it's quadratic. I can't spell this in my life, man. Okay, quadratic. Conceptually, it's quadratic because we're kicking a ball. It's landing on this roof, but we're solving for time, right? The time it takes for the ball to hit this particular height, 12 meters, it does that at 2 locations. It does it on its way up, and it does it on its way down. So we're going to get 2 times. We're going to get an earlier time from this solution and a later one. And our actual answer will be the later time, because that's when it hits the roof. So let's go ahead. So 1/2 at squared plus v naught yt minus so 1/2 a is going to be the minus 4.9 because a was minus 9.8, right? And that's t squared. Our v naught y was just what we solved for, 19.1. And then this was minus 12. So if you plug this into the quadratic formula, t equals minus b plus or minus the square root of b squared 4ac over 2a, where a, b, and c were 1/2 a, v naught y, and y final. And if you plug in like this, here's our plus minus. To minus 4.9, you will generate 2 times. You'll generate 0.78 seconds or 3.11 seconds. And again, these correspond to these 2 times. One when it's going up, and then one when it lands on the building. So it is the later time. Okay. So t equals 3.11 seconds. That's how long it takes. We still need x final. So x final equals x initial plus v naught x times time. V naught x we haven't even solved for yet. Also that was 0. This is just v naught cosine theta. But because we were using 45 degrees, v naught x actually equals v naught y. So this is also 19.1 meters per second if you plug it in. So x final equals 19.1 meters per second times our time, which is 3.11 seconds, which is 74.3 meters. Okay. And that's so this is how you tackle these quadratic questions. Okay. They're a little bit more complicated than the other ones because you have a quadratic formula to deal with. But that's the way it goes. Okay. So thanks, and I'll see you in the next one.